So today we're going to finish up the lab. The quiz over projectile motion is actually going to be tomorrow because Friday got all screwed up the first block, and so anyway, so that's going to be tomorrow. It's going to be like literally the front of one page. That's it. Okay. So there's going to be like a limiting problem, a ground-to-ground problem, that type of thing. Okay. So go back. You've got all your assignments back. Basically, if you can do all your assignments, you can do that and understand the labs. You're fine. Okay, so here's what we've got today. You should have those last 4 trials to do, okay? And so here's the key assumption that we're going to make initially, is that whatever the weight is of whatever hanging down is what's creating the centrifugal force, okay? That's the key assumption that we're going to make initially. So when you look at centrifugal force equaling mv squared over r, we're going to change these 3 different variables. We're either going to change the amount of centrifugal force and keep the mass and radius constant. That's what's happening on your first 4 set of trials. Then we're going to keep the centrifugal force constant and then change the radius. That's what's happening on the next 4 set of trials. And then in the last 4 set of trials, you're going to keep the centrifugal force constant and the radius constant, and then you're going to change the mass. Okay? And that's the mass of the stopper. So you're going to manipulate those 3 variables: centrifugal force, mass, radius. So here's what you're going to look at. So on the back side over on page 2, where it's got the graph. Okay? So what you're going to do is you're going to graph, and I tell you explicitly how I want this. You're going to plot velocity on the y-axis and centrifugal, velocity on the x-axis. So you're going to have centrifugal force here, and you're going to have velocity here. And I tell you, this graph is going to start from 0, 0. So what that means is that you're going to have like 1, 2, 3, whatever these values are. And then this is going to be like 1, 2, 3, however you set it to scale. Okay? Since this is specifically going to start at 0, 0, you can't like change these scales. They don't have to be identical, but you can't change the scales once you've established them. So if you look at this mathematically, this ratio of mass of the stopper to the radius of the stopper is a constant because those 2 numbers are the same. You're not going to change the mass of the stopper, you're not going to change the radius. So you could actually get this constant. You don't have to, but if you wanted to, you could. That part of the equation isn't going to change. So this is basically nothing more than F equals kv squared, which is y equals kx squared because you're graphing velocity on the x-axis. So if you were in math class and I said, hey, I want you to draw a graph y equals kx squared, what would that graph look like? It's a quadratic function. So that's what this graph should look like when you get done. Now, if you get like 3 points that are really nice, and then you have a weird outlier, don't go, oh, okay? No, you chapped up this experiment. If you have time, go back and redo that one, okay? But you should be able to smooth out that curve. The other thing that you're going to see, because all of these are dependent upon velocity squared, none of these should be linear functions, because they're all dealing with velocity squared. So you should not have a single linear function on any of your 3 graphs. So here's how I want this answered. So when you go to question number 1, hey, there's the graph that you're going to draw. Draw this graph as big as you can. Okay, don't draw this tinky little postage-sized stamp. Okay, draw that graph as big as you can. Then I'm going to say on question number 2, using this equation, which variables are held constant and which were changed. So when you look at this, this is trials 1 through 4. Of these 4 variables, which 2 were held constant? Mass and radius. Okay? So that's how you're going to answer question number 2. Which is, hey, what variables are constant? Oh, mass of the stopper and radius. Which ones were changed? Don't make this difficult. The interchange is the amount of centrifugal force and the velocity. That's it. That's all you have to say. So on questions 2, 6, and 10, make sure that you have mentioned all 4 of those variables in some combination of either which ones are changed or which ones are constant. Now, when you get to number 3 on the basis of your graph, explains the relationship between velocity and centripetal force. So ideally, you'd be able to look at this and go, oh, it's a quadratic relationship between velocity squared and centripetal force. If you just want to say, as your velocity increases, your centripetal force increases, I'll accept that. But technically, it's like it's a quadratic function. Now, here's the heart and soul, what I want you to understand when you get to question number 4. When I said, explain your answer to number 3 in terms of this equation, F equals mv squared. So, here's what I'm looking for. There's 2 ways, there's any number of ways you can approach this, but here's the easiest way. Here's what I would expect to see. You would say something like this. All you have to say is, like, since mass and radius are held constant, as you increase the centripetal force, the velocity has to increase as well. Okay, so that's one option. The other option is you change it up a little bit and you go, oh, since I'm increasing the centripetal force, the velocity has to increase because mass and radius are constant. I don't care what combination you put that in, but when you answer questions 4, 8, and 12, make sure that you mention all 4 of these variables: centripetal force, mass, velocity, and radius. Make sure that you talk about all 4 of them. Now, if you go back and read your explanation and you've only mentioned 3, just don't put "and mass" at the end. Okay? It has to fit within the context of your explanation. Okay? So there's that. Make sure that you mention all 4. Now, down below, when you get to question number 13, for trials 4, 8, and 12, calculate centripetal force. Now we're going to see if the data actually matches up with the theory. So what should happen, like on trial number 4, you had a 0.4 kilogram mass that was suspended by the end of the string, right? That's what was suspended. So when this thing is being pulled down, if you multiply that by your gravitational acceleration, you get 3.92 newtons. So in theory, that's what the value of your centripetal force should be, is 3.92 newtons. In theory, that's what it should be. Okay? So what you're going to do is that we're going to use this as our theoretical value. So this is what it should be. So when you get to question number 13 in trial number 4, you're going to take 3.92 newtons, which is your theoretical. Now you're going to divide that, or you're going to figure out what your actual experimental data was, based upon the mass of the stopper, the radius, and period. So with this one, you're going to go mv squared over r. So you're going to go to trial number 4. You take the mass of the stopper. Don't use the 0.4 kilograms, because the 0.4 kilograms wasn't what was being swung around. Okay? It was the mass of the stopper. You're going to trial number 4. You're going to find the velocity of your stopper. And you know that radius, which is 0.7 meters. So you're actually going to calculate your centripetal force based upon your data. This is going to get you a number. So that's going to go here, what you're going to get from mv squared over r. Go to trial 4. I don't want you to do this on all 12 of these. You're only going to do it on trials 4, 8, and 12. Then you're going to take that, and then you're going to divide that by 3.92 newtons, and then multiply that by 100. Now, on this stuff, I have no answer key. The only thing I can grade you on is your work. And this is what more and more of you are getting sloppy on your explanations in terms of units, equations, and things like that. This is about conveying information. This is not about numbers blissfully written down, and I have no idea what they are. You have got to pay more attention to the fact that you are conveying information. This is not about a number. Labs are about a process. Okay, that's one of the most important things that you have to understand. So, because everybody's data is different, this is the only way that I can verify what you did, is if I see that work. So, you're going to do that in trials 4, 8, and 12. There. Now, when you get to page 3, or page 2, depending on how you count it, question number 14, here's what you're going to do. You're going to calculate the actual centripetal accelerations for trials 4, 8, and 12. So basically, all you're going to do to get that centrifugal acceleration, what I would recommend is that you use v squared over r. So you're going to go to trial 4. You're going to you've got the velocity. You've already found it. You're going to square that, divide that by the radius of 0.7 meters, and you're going to get your centrifugal acceleration. Now, g's are a multiple of 9.8 meters per second squared. So like right now, you all are pulling 1g, which sounds very scientific. Oh, I'm pulling 1g. Woo! Good for you. So is everybody else. You're not special. Nothing personal. So, but what that means is that you're used to lifting your arms under 1g. When you get up in the morning, okay, and you raise your head off the pillow, you're raising your pillow, you're raising your head off your pillow under a load of 1g. That's what you've experienced your entire life. We live in a 1g world. Now, it'd be really weird, but let's say overnight, the mass of the earth greatly increases. And you wake up tomorrow morning, and now we're all living in a 2G world. So what that means is that when you go to lift your head up in the morning, it's going to feel twice as heavy. You lift your arms, it's going to feel twice as heavy. Instead of having like a 32-inch vertical, you're going to have a 16-inch vertical. Okay? So everything's going to feel really, really, really heavy because your acceleration has gone from 9.8 meters per second squared to 19.6 meters per second squared. So everything's going to feel really, 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 really heavy. So to get the value of g's, you take your gravitational, your centrifugal acceleration, and you're going to divide that by 9.8 meters per second squared because it's a multiple. So if your centrifugal acceleration is, say, 30 meters per second squared, that means that you would be about 3 g's. Because if you take 30, roughly divide it by 10, you get about 3 g's. So to get the g's, and I even tell you this, divide your acceleration by 9.8 meters per second squared, because it's a ratio. Now, when you get to number 15, we're going to calculate the amount of centrifugal force needed to keep our rock in orbit around our star. It's going to be a pretty big number. So on 15 and 16, what I would recommend is that you use this. Mass 4 pi squared r over t squared. You can calculate the velocity of the Earth separately and then use mv squared over r, but it's a god-awful amount of work. I don't recommend it. Okay? Just use this directly. Now, you've got the mass of the Earth. That's simple. But what units does that radius have to be in? Meters. What did I give the radius in?
Kilometers.
Kilometers. Guess what? You might have to do a simple conversion. Now, how long does it take for our rock to make one orbit around our star?
365 days.
365 days. You think you can leave that as 365 days?
Sure am.
No, because if you do, you get kilograms meters per day squared. Okay? Check me if I'm wrong, but I don't think that's how we measure newtons, which would be really weird. Okay, kilograms meters per day squared. Okay, so now when you convert years into seconds, okay, when you do this conversion, don't round this value of time. Okay, when you're doing that conversion, because this is exactly 1 year, it's 365. If you really want to get technical, it's 365.25. Okay, so when you do this conversion, do not round that value of time. Okay, do not round that value of time. Now, how do we know that there's a centrifugal force acting on our rock?
So we're not flying off into space.
Yeah, because if we don't have that force, what's going to happen? We don't orbit our star. Bad things are going to happen. Okay? Now, what you're going to do on 16 is you're going to find the centrifugal force needed to keep Al, okay, in orbit, or excuse me, basically on Earth as the Earth is spinning. So right now, we're traveling on a spinning rock. We don't want to travel in a curved path. We want to fly off in a straight line. So there has to be some amount of centrifugal force that's acting to hold us in, right? So what you're going to do on number 16 is you're going to calculate the centrifugal force needed to hold a 70-kilogram person on the Earth as we go around and move in a circle. So how long does it take for our rock to spin once on its axis? 24 hours. So on 15, you're going to use a period of 365.25 days if you really want to get picky. And then on 16, you're going to use a period of 24 hours. Okay? Now, when you get to 17, you've got this rubber stopper that's moving around in a circle. You're going to go to trial number 1, okay? And you're going to figure out all the forces acting on that rubber stopper. You're going to set up a scale, and then you're going to draw those vectors. And you're going to show me that scale. Going, oh, 1 centimeter equals 1 Newton. These are going to be pretty small numbers, so you might let like 2 centimeters equal Newton or 3 or 4, because these are going to be pretty small numbers. So make sure I see exactly what that scale is, and make sure that you draw that to scale with a ruler and pointing those forces in the direction that they're acting. Okay? Cool with that? We're good? Okay. Now, stop that for a second. Assignment is also due tomorrow. It's relatively short. I'm actually going to get you started on a lot of these. So let's talk about question number 3 at the top. Because I'm going to show you 2 different ways you can work question number 3 at the top. Because otherwise you read this and you want to curl up in the corner in the fetal position and suck your thumbs. So, and I want to avoid that at all costs. It's just not going to be pretty. So, you got an airplane going around in a circle. It's made to go faster as more wires played out until both the speed and the radius of the circle are constant, double their original values. So here's the basic story. So here's this aeroplane, right? And airplane, and it's going around like this. Is it undergoing centripetal acceleration?
Yes.
How do you know?
It's changing direction.
Moving in a circle. Otherwise, if it wasn't, it would
Line, a straight line.
Okay. So, there's 2 ways you can calculate centripetal acceleration. One is 4 pi squared r over t squared, and the other one is v squared over r. Which one do you think we should look at? Why?
Because that's
What am I asking about?
the
The radius and
speed.
velocity, speed, how fast it's going, right? Okay, so let's choose this one. If I talked about radius and period, I'd talk about this one. So there's 2 ways you can do this. One is what we call smash mouth physics, okay? In smash mouth physics, you actually make up numbers. So what would be the easiest velocity we could pick?
1 meter per second.
1. Okay. That's going to be 1 meter per second. And that's going to get squared. What's the easiest radius that we can pick?
1 meter.
1. Okay? So check my math. If I take 1 meter per second squared and square that, and I got 1 meter, that should be 1. So that's my centripetal acceleration, right? Okay? If you don't believe me, plug it into your calculator, and I think you'll find that I'm right. Now, then we're going to look at what we call AC prime. Okay, so this is the new set of conditions. So instead of 1 meter per second, what's going to become the speed of the plane? 2, because you're told that it doubles. Okay, so that's going to be 2 meters per second, but that's going to get squared. Now, what are we going to do with the radius? So that's going to become 2 meters as well. So 2 squared should give me 4 divided by 2 gets me. So what happens to my centripetal acceleration? It doubles. Okay? There you go. Now, that's what we call smash mouth physics. That's putting numbers into the equation and figuring out what happens when you change the system. That's smash mouth physics. Now, the more elegant approach is this. You go, okay, that's my relationship, v squared over r. Okay? I don't care what it is, it's just a velocity in r and divided by a radius. So my new one, how can I show that this thing gets doubled? 2v, but that's going to get squared. And then what am I going to do with the radius? 2r. 2r. Okay? So I get 4v squared over 2r, which becomes 2 times v squared over r. So no matter what happens to your centripetal acceleration?
It doubles.
It doubles. So this is the more elegant approach, and it's actually easier. Okay? But if you don't like this and you go, Mr. Burkamp, I need numbers, fine. If you need numbers, knock yourself out. Make up some numbers, but choose wisely. Don't choose like pi meters per second divided by 0.005, okay? Choose numbers that are easy to work with. Okay.
You always choose. You just always choose one.
Huh?
You just always choose one.
Yeah.
Okay.
Or 10, or 345.7. Whatever works for you. Okay. Now, let's talk about question number 9. Okay? Let's talk about question number 9. Or down below problem number 9, whatever it is. So I'm guessing, hopefully in Chem 1, you all were exposed to the centrifuge.
Yes.
Spins around, goes really, really fast.
Oh, yeah.
Okay? Huh?
Separates four.
Yeah, well, basically it creates a false gravitational field. So you use it to separate solids from liquids because it's an intense gravitational field. So you're told that this thing spins at 5,000 revolutions per minute. Okay, so that's the number that you've got. So you got 5,000 revolutions per minute. Now here's the new thing that you need to know. When you have revolutions per minute, or an event per unit of time, this is what we call frequency, okay? So it's an event per unit of time. So like, let's say you work at a job and you get a paycheck every 2 weeks, okay? So your frequency of your paychecks would be I get one paycheck per 2 weeks. That's an event per unit of time, okay? Now, this is 5,000 revolutions per minute. So anytime you have an event occurring per unit of time, that's frequency, okay? Now, but here's the trick. First off, this is in minutes. Are we going to work in minutes?
No.
No. But if I take 5,000 revolutions per 60 seconds, then what? Now what do I have? Revolutions per second. That's something I can deal with. So somebody take 5,000 and divide that by 60. It's 80 something. 83.3 revolutions per second. Now, this is why you have to pay attention to the units. This is revolutions per second. Now, on your equation sheet, I've got this handy-dandy little relationship that says period is the inverse of frequency. What that also means is that frequency is the inverse of period. So if you think about this, this is why this works. If you're making 83 revolutions per second, guess what? It doesn't take very long for each revolution to take place because you're making 83 of these per second, right? Okay? Makes sense. So what I would recommend in a situation like this, I'd look at 4 pi squared r over t squared. Don't go through and find the velocity separately. You can, but it's a god-awful amount of work. Don't do it. Okay? This is why we came up with this relationship here. So here's the trick. This needs to be in seconds per revolution. This is revolutions per second. So what can I do with this to get seconds per revolution?
1.
Yeah, take the inverse of it. So if I take 1 over, so let's make sure everybody has this number. So take 83.3 revolutions per second and take the inverse of that. What do you get? Should be 0 point something.
0.1012.
0.0120?
Yeah.
Okay? Seconds per revolution. So this is where the magic happens. Okay? Because when you take the inverse of this, the revolutions stay down here, the seconds flip up, and then it becomes seconds per revolution. This now is the period. So this is what you can slam into this equation up there. Okay? So period and frequency are inverses of each other. So what that means is, because if you think about it, even look at our Earth. Okay? What's the frequency of a revolution around our star? 1 revolution per
year.
No. This is around our star. 1 year, okay? We have 1 revolution per year, or 1 revolution per 365 days. which means that, guess what? Each day is a small portion of that revolution. Okay? Now, if you think about it, it's kind of cool. It takes us about 365 days to go around our star. How many degrees are in a circle?
360.
Around 60. So that means that we go about a degree a day as we go around our star. Okay? So it's kind of cool. It's like coincidence. It isn't like we planned it that way. All right? We just kind of have to work out. If we were to go a little faster, it would be an exactly degree a day. That's pretty crazy. Now, when you get to question number 8, got a hammer thrower or track and field whirls around at 2 revolutions per second. So is that 2 revolutions per second frequency or period?
Frequency.
That's frequency. Okay? That's frequency. Hunter.
Period going for R.
No. R, no.
So does
No.
period go for?
That's just radius. Okay?
Yeah.
Radius has nothing to do with time. Okay? So when you take the inverse of that only goes in here for period. Radius has nothing to do, no, bad. No.
The period's
Bad.
on.
Big T equals period.
Yes, big T equals period.
Alright.
And that's the inverse of frequency. Does that make sense?
Yeah,
Okay, we're good? Go, oh, radius, bad.
I know it's.
Okay, I am done. Okay, so you have the rest of the time, get your data. When you get done, please make sure everything gets put away. The lab and everything is due on tomorrow. You have the next hour. Be free.